Good morning or good afternoon, depending on where you're based. My name is Niels Verdijk, and I will be the host of your of this webinar. I hope you can all hear me properly. If not, please let me know in the chat that I can still change some settings. All right, let's dive into it. Today we'll be talking about enhancing cooling performance using generative design. We'll be looking more in detail in what or how your manufacturing settings have an impact. We'll be looking at 3D printing, die casting, and CNC milling in more detail. Okay, that's it for the general introduction. Next, I will introduce the different manufacturing techniques in a bit more detail. So diving deeper into the three highlighted here. And then for all of them, I'll dive a bit more into detail into the pros and cons. That's the more technical side of the webinar. Afterwards, we can then focus on switch to applying it on a case study. If you have any questions, we'll towards the end of the meeting, webinar, we will answer them in the Q&A section, and let's try to keep this all within the 30-minute mark. But starting with the beginning, a bit more into detail what the different manufacturing techniques mean. The one that you're very familiar with, I'm very sure about, and that's also very popular right now, is 3D printing or additive manufacturing in more detail. There's a wide variety of different additive manufacturing techniques. For example, with metal, you can go for SLM or selective laser melting or LPBF. But you also have, for example, for home printers, you have fused deposition material, where plastic or polymer is being deposited on a table. This manufacturing technique basically allows for very complicated structures, allows for three-dimensional objects to be generated, and has a lot of design flexibility. For our heat sinks, for example, typically they're made out of metal, and with metal 3D printing of metal additive manufacturing, there is always a small layer of metal powder, where the laser then either melts or sinters the material or the powder to the rest of the components. And you build in the component layer by layer. Then we have die casting. For die casting, it's relatively simple, I would say. You create a mold, and your metal will be heated up until it's in liquid phase, and then you pour basically your liquid metal into your mold. Of course, you have to make sure that the mold or the metal inside of the mold cools down as uniformly as possible. Otherwise, you'll have some tensions because of uneven cooling. But in general, molds can be used multiple times. So you typically see them for high volume production. And then we have CNC milling. CNC milling is a very precise manufacturing process where you start off with a single block of metal, and then the milling tool basically chips away the parts of the metal block that are not needed. So basically, the milling tool will follow the channels. Will basically create the channels out of your full solid block. Okay, now that you know a bit more about what these manufacturing techniques are, let's delve into what the pros and cons are. Die casting, starting with die casting, because you have to create a mold, it's quite an investment, or quite expensive to make. But if you manufacture the same piece a bunch of different times, so for mass manufacturing, die casting becomes very, very interesting. It's in the long run, it's quite cheap per unit if you have in a mass manufacturing capability. CNC milling and 3D printing, on the other hand, they typically are reserved for more more in prototype stage. It's quite expensive to make for lower batches. It's perfectly fine, but for mass manufacturing, the cost per unit is quite high. So typically for mass manufacturing, you go with die casting. Or for prototyping, you typically see the CNC milling or 3D printing being used. Then if you look at design flexibility, for 3D printing, you allow for a very complicated structure where the shape can vary over the height. You can have a true spaghetti of cooling channels. While for CNC milling and die casting, especially die casting, since you have to get it out of the mold, and CNC milling as well, of course, because the tool has to get everywhere. The milling tool has to get within the block. The design flexibility is much more limited. Typically, you see more two-dimensional structures being generated using CNC milling and die casting. So in short, 3D printing, more design flexibility, but at a higher cost, while die casting, less design flexibility, but at a lower cost. And now it's a bit of the trade-off, and that's where generative design software can help you, of course, is the potential benefit in thermal performance, because with the added design flexibility, you of course have added thermal performance. Does that outweigh the costs of increased manufacturing costs? And that's something that in generative design software you can try to figure out. So in generative design software, in a first stage, you typically go with a fast, or what we call the fast concept generation, where at an early stage you try just a bunch of different concepts, a priori defined shapes like pins and fins, or TPMS structures like gyros, etc. If you want to know more about it, feel free to rewatch one of our previous webinars. The fast concept generation phase, the word says it, can quickly generate a bunch of different designs, giving you insights into how a change in design affects the performance. For example, if all the pins, which can be die cast, for example, perform much worse compared to TPMS structures, which are exclusive for 3D printing, you can basically have to go with 3D printing if if your thermal requirements are very, very strict. And then you can move on once you have generated all of those concepts. You know what works well. You can then move on to a detailed design, again, be it for 3D printing or for CNC milling. The thermal analysis phase, not really suited for within the scope of this webinar, as typically if you have you design for a given flow condition in the thermal analysis phase, you then, for example, do run additional simulations on different flow rates to see how it behaves. So not really in the scope of this webinar. Okay, you might think it's quite, in generative design softwares, it's quite difficult to set up such a problem, while in reality it really is not. So in the first step, you create your CAD files. You do that in your preferred CAD environment, be it NX, Siemens NX, or Autodesk Inventor, or any of the other CAD environments that are out there. You prepare your geometry, and then you upload the geometry to your generative design software. Next, you set the solids and fluids. So in this phase, you basically let the software know, is it aluminum or copper, for example? For liquids, or for the fluid, sorry, is it air cooled, or is it water cooled, or water glycol cooled? That's something that you specify here, because that, of course, greatly impacts the thermal performance as well as the design that will come out. Next, you set the boundary conditions. So you define what the inlet and outlet conditions are, what the heating powers are, etc. And of course, you also set your targets, basically what you want to optimize for. Be it maximize heat exchange efficiency, constrain the pressure up to make sure that the pressure doesn't rise to infinitely high, for example. And typically, you can have a mix of different targets to suit your basically what you want to get out of it. And that's it. Once you provide all of those details, the generative design software will then take over and it will start computing for you. And once it's ready, you can download results, you can analyze the results, and see what works for you. Okay, I think that's more than enough theory for now. Let's now move on to the case application. It's a relatively simple geometry, so it's a double-sided power inverter, where we have here the housing on the left, onto which two heat sources are placed, one on the top and one on the bottom, both producing the same amount of heat. We have an inlet on one side and an outlet on the opposite side, where the flow rate that enters through it is fixed. And then most importantly, we also define then the design domain. So the design domain is the volume where the generative design software is allowed to create structures so it can add those intricate patterns. I will be using aluminum for all the solid materials because it's a relatively cheap material to work with. Okay, I will now switch to Coldstream to basically showcase how it works. So once you log on to Coldstream, you will then see most likely work in the projects view. That's where you will do all of your work. I will then move to the project for this webinar, like so. Yes. And inside of your project, you then have all your cases that you want to work on. So the cases, as in the engineering problems that you want to solve. And let's start then with setting up a fast concept generation case. Like so, this case already has a geometry, so I won't bore you with that. And as I mentioned, once the geometry is available on the platform, you simply click on each of the entities and start filling in the information. So if you start here with the housing, so it's everything in blue here, you then define what type of region is this. Is it a solid or a fluid? In our case, of course, it is a solid. And you can then specify out of what material it is made. So for us, it's of course aluminum. Then we have our two heat sources, one on the top and the other one on the bottom. Again, from the drop down, you select the type of bounding condition you want to impose. We'll use here the heated wall, allowing us to specify a given heat that enters through the entire surface area. And that's 150 watts of energy for both. And then as our goal, these are our heat producing components, of course. We want to minimize the temperature, or equivalently, we want to maximize heat exchange efficiency. Okay, so that's our housing. Let's then move on to our coolant. So our coolant, of course, is a fluid where we'll be using water glycol as a coolant. Then we have an inlet on one side where we fix the flow rate to 2.5 liters per minute at an inlet temperature of 45 degrees Celsius. And just to make sure that the pressure loss doesn't increase to something unrealistic, we constrain the pressure up to 400 Pascal. So basically, we let Coldstream know whatever it designs, the pressure between in and outlet can never exceed 400 Pascal. Okay, so what comes in must go out, of course. For that, we have the outlet on the opposite side, which is just a regular pressure outlet condition. Then for our design domain, so here you can start dictating in the fast concept generation phase what kind of shapes you want to consider. For example, if you go to CNC milling, you can have circular or diamond-shaped pins. You can also have rectangular fins if you like. Then you have the 3D printing exclusive structures like TPMS structures. For example, gyroids or lidinoids, whatever you want to consider. And for die casting, you again have circular pins or rectangular fins. Once you provide all those shapes that you want to consider, You specify as well, of course, the constraints and as well the material that will be used to make those components. And that's pretty much it. Once you provide all the data, Colson will, or your generative design software, will be able to start computing. Let's immediately jump then to some results. I ran a verification simulation with best performing designs using die-cast pins and the best TPMS structure. And if you then put them in the comparison view, we can then easily see how they perform with respect to one another. So the three leftmost columns are the die-cast design, so the max, mean, and minimum temperatures of all our entities. And the right, the three rightmost columns are the, again, max, mean, and minimum temperature of our best TPMS structure. And here we can see, if we look at the heat sources 1 and 2, our main interesting heat, or our main point of interest. Perhaps I'll look at it in charts format, like so. Yes. So if you look at the maximum temperature, the die-cast design, so that's the dark green one, performs worse compared to the light green or light yellow one, I would say, which is our TPMS structure, which is of course to be expected. With 3D printing, we expect a better design to come out, and it's showcased by how much. So for this particular case, the difference in performance is only about a degree, but on a 7-degree heat up, that can already equate to a 15%, more than a 15% improvement in thermal performance if you go from die casting to 3D printing. And then it's a bit up to you as a designer. Does that outweigh the costs of the additional cost of manufacturing if you go with 3D printing? Okay, so this is basically what it would look like for more conventional cooling solutions. Let's say if you then move on to a detailed design, so by using a topology optimization to extract the maximum performance out of it. The input is almost identical. So here I'm setting up a case for a detailed design, where again you have your housing and your two heat sources with the same targets. We can have our coolant volume, our inlet and outlet with again the same constraint. But here on the design domain, you specify just your manufacturing technique. Because in the detailed design, you don't have to fix any conventional shape. You just say the shape needs to be manufactured by any of the available manufacturing techniques. Again, you specify the manufacturing settings themselves, and then you let the software start running. And if you then have a look at the best performing 3D shape, we can then have a look how your manufacturing settings impact the design. Yes, here I'm showing the fluid domain, so basically the negative space of your salt structures. Bear in mind this is 3D printing, hence why you see a very complicated network or spaghetti of of channels. And if you look at the side profile, we basically see that in this particular case, our generative design software found it beneficial to split the flow top and bottom, which makes sense, of course, because that's where our heat sources are placed. If we then run the same case, but with CNC milling in mind, again, it's a detailed design, so no conventional cooling solutions are limiting the design freedom. We again see a intricate pattern of cooling channels, but as you can see immediately, the cooling channels are perfectly two-dimensional. There is no, with the CNC milling manufacturing technique, there is no variability over the height, because it's simply not possible for the tool to get there. And if you then have a look at the die casting design, view results, and then load in our fluid domain again. In my opinion, that's the easiest to have a look at. We again see a intricate pattern, but again, no variability over the height, simply because otherwise it can't get out of the mold. Okay, so that's the basically how the manufacturing settings impact the design. Let's now compare them. So remember, for the conventional solutions, we saw that, that there is basically a 1 degree. Oh no, sorry, that's not what I want to do. We saw that there was a 1 degree difference in performance out of a 7 degree heat up. If we look at the temperatures again, so the green one is the 3D design, so the spaghetti of channels. The light, or the purplish blue is CNC milling, and then the reddish one is die casting. And again, we see a more or less 1 degree difference in performance when we compare a 3D design to a die casted or a CNC milled design. So CNC and die casting with the settings that were provided return a very similar design, or design with similar performance measures, while the 3D design outperformed it by more than 50%. And again, it's up to you then to decide as a user or as a designer, does that 15% improvement in thermal performance, does that outweigh the costs of using 3D printing? Okay, that's everything that I wanted to cover for the Q&A session. Where is my, let's look back to my slide deck. It looks like it closed for some reason, so let me quickly open that again, and then I can start sharing my screen again. My apologies for this. And then I can start sharing my screen like so. Yes. Okay. Are there any questions? Feel free to put them in the chat box. Okay, so we have a first question coming in. And the question that comes in is, okay, so in the example software that I showed in our call stream, it looks like only 3D printing was an option, but there is no way to select is it SLS or SLM, because of course that has an impact on the design. And there's a good reason for it. So if I go back to call stream here, yes, and then I'll go to the libraries page. So the manufacturing settings are basically a group. They're not one specific setting. You have a group of different settings that belong, or that can be categorized as part of this, for example, 3D printing. If you have an SLS machine in mind, for example, you can simply insert those constraints by creating your own custom manufacturing settings. So, for example, with 3D printing, what you have control over is RF min and RC min, where RF min is basically your minimal the minimal printing resolution that your SLS machine, I'm saying SLS, but that your machine can handle. Same with RC min, there's a minimal channel width size. So just make sure that you have enough room for depowdering. You also have then the equivalent maximum constraints, should that be of interest to you. You also have control over the overhang angle. By default, it's 45 degrees. But, in the 3D in the manufacturing world, that's also the default. You also have control over the unsupported length, both cantilever and bridge. And that's why how you can fine-tune the 3D printing settings to make sure that whatever Colton outputs will meet your manufacturing machine. Same with die casting. If I go to this one, for example, with die casting, you again have a wide variety of different parameters that you have control over. Again, RF min and RF max, so the minimal and maximal structure width size. Especially RF max is quite handy because you don't want it too wide, otherwise it's almost impossible to cool the center. And because remember, it's quite important that the entire block cools down as uniformly as possible. I also have control over RC min and RC max, but for die casting, of course, we have filter radii at the root here, BRI, at tip, BRO. Very important, you also have control over your release angle. The bigger the angle, the easier it is to get it out of the mold. If you have a very wide angle, especially if you want very deep structures, you don't have lots of room for don't have too much room for lots of structures. Well, if you have a small angle, then you maximize or potentially maximize the number of structures you can add, but it's a bit more difficult to get it out of the mold. I hope that that answers your question, but if not, please let me know. Looking at the time, let's start moving towards the end of the webinar. If you still have questions, don't hesitate to put them in the chat. So yeah, if you want to try Colton for your own, feel free to visit our website, diabetics.com/utility/try now to get access to our trial account or to our try now account. Sorry, where you can have a look at old projects that we did. Or if you want to know more, you can contact the team by either emailing to info@diabetics.com, or you can simply call us by ringing this number. Okay, that's everything that I want to cover today. I hope it was interesting, and this is the last webinar of the year for us. So I wish you all a very pleasant Merry Christmas, sorry, and a very happy New Year. And I hope to see you in the next year. Take care. Bye-bye.